Hello everybody, it's Mr. Ray here with our next lesson in grade 12 vectors. We're going to finish up our introduction unit on vectors with a lesson on it's called linear combinations and spanning sets. So before I can really talk about that, I guess we need to define what that actually means. So a few definitions. These are mostly new except for the last one. So collinear, that's when basically two vectors, call them u and v, are collinear if and only if it's possible to find a non-zero scalar such that u is equal to a scalar k times v. Collinear vectors must be parallel. So collinear is just another way of saying you can create one vector from the other by using a scalar multiple. So by definition, collinear has to be parallel as well. Okay, a linear combination of vectors, that actually just means it's a new vector formed when you take two vectors or more, multiply these vectors by scalars and then add them together. So just combining scalar multiples of two or more vectors to create another vector. And spanning set is kind of what this lesson's based on. It's a set of vectors that can basically define every single vector in that vector space. So we'll talk about that in just a few seconds. And a plane, finally, that's a flat two-dimensional surface that extends infinitely far. So we really only talk about planes in R3. I guess the XY grid is a plane itself, but we don't really talk about planes in R2 since there isn't really much to talk about in terms of multiple planes and comparing planes because there's only one plane and that's the XY grid. Okay, so the key concepts, we're talking about spanning. So in R2, if you have a position vector OP that consists of components A, B, that means you can multiply basically the I hat vector by a scalar A and the J hat vector by scalar B. You could create any vector you want in two space using those two vectors, a linear combination of those two vectors. So basically what we're saying is the vectors I hat and J hat span R2 because you can uniquely write every vector in R2 as a combinations of I hat and J hat, these two vectors here. And if we extend that to R3, if we have another position vector OP, this time we've got the three components, and basically what this means is if we have a scalar multiple of I hat plus a scalar multiple of J hat plus a scalar multiple of K hat in R3, we can write any vector as a unique combination of those three vectors. Okay, so those aren't the only spanning sets. We call these spanning sets because they span a certain vector space. There are other sets of vectors that can define R3 or R2 or a plane. And with R2 it's pretty simple. Basically any pair of non-zero, non-collinear vectors will span R2, which means as long as you don't have two vectors that are, well, they're non-zero, but they're also not scalar multiples of each other, you can write any vector in R2 as a linear combination of those two non-collinear vectors. And in R3, again, so this time we're talking about a pair of vectors. Any pair of non-zero, non-collinear vectors will span a plane in R3. Okay, so as long as those two vectors that we're combining are not collinear, they're not parallel, you can't write one as a scalar multiple of the other, then those two vectors will span a given plane. and we'll do an example question involving this. This means that every vector in that plane, so if this blue rectangle is the plane, we could create any vector we want that lies on that plane by the linear combination of the other two vectors that are also on the plane. Okay, so that's basically the definition of spanning sets and linear combinations. So let's do a little bit of work. Okay, example 1. Are the vectors A and B collinear? So A has components 2, -4. B has components -6, 12. There's a couple of ways to do this, and then there's just kind of common sense. So I'll show you these two methods, and you can decide how you want to show this yourself. So basically I can see that if I wanted to find vector B in terms of vector A, so I've got, here's vector A, I'll put its components. So I know vector B is -6, 12. So I know that if I want to create at least the x component of vector B, I have to multiply vector A by -3. Okay, so I know that multiplying these two together will get me the x component of vector B, but will it also get me the y component with that same scalar? So I try it out. That gives me +12, and yes, that gives me vector B. So now I can say that vector B is equal to -3 times vector A, and that is showing that B is a scalar multiple of A, which proves that they're collinear. Okay, the other method, I know a lot of students will use this. It's it's a lot more not thinking about it. It's just very mechanical. So if you create two ratios of the two vectors, so x1 over x2, we want to prove that they're equal to y1 over y2. So x1, y1 will be the components of one vector, x2, y2 will be the components of the other vector. So in our case, I've got A is 2, -4, so I put those on the top where the x, y, y1 is, and we have -6, 12. If I reduce these, I get -1/3 is in fact equal to -1/3, so that proves that they are therefore collinear. Okay, so that's the two methods. So you could do the ratios, prove that the ratios are equal, therefore they are collinear, or you could just try to find the scalar that does in fact turn one vector into the other. So therefore they would be collinear in both cases. Okay, so whichever way you prefer is okay. Now, this one, we want to represent a vector as a linear combination of two other vectors. So what we're trying to show is that we can create this vector x, which has components 4, 23, as a linear combination of these two, which means there would be a unique scalar that multiplies the first vector added to a unique scalar multiplying by the second vector that will create that vector x. So we don't just kind of guess at this, sort of like we almost did up here. We actually create an equation to find those scalars. So for example, the first vector, -1, 4, if there's some scalar a that I multiply that by, and then add that to a second scalar multiplying the vector with components 2, 5, I want to be able to create the new vector x, which is components 4, 23. Okay, and you can see I'm actually going to create two equations out of this, just by an equation for the x components and an equation for the y components. So if I multiply and get to get the x components, I got a times negative 1, which is negative a, and plus 2b, and that should give me the x component of our desired vector, which is 4. Okay, so that's our first equation. And then the second equation will be to get the y components. So I would have 4a plus 5b is equal to 23. There's our second equation. So you can tell this is a linear system. So what we want to do is find the values of a and b that make both of these true. So we can use the techniques we've learned in grade 10 and 12. I think we skipped it in grade 11. So what I'm going to do, I can see if I multiply the first equation by 4 and then add it to the second equation, I'm going to be able to cancel out the a's. So I'm first going to do 4 times equation 1, which would be negative 4a plus 8b equals 16. So that's my third equation, which comes from my first equation. And now I'm going to add equations 2 and 3 together. So 2 plus 3. So adding this way. So 4a plus negative 4a, that's 0. 5a plus 8b, that's 13b. And 23 plus 16 is 39. And we can divide both sides by 13 and get that b is equal to 3. So we have our first scalar. So now it's just a matter of getting the second scalar by using the correct value of b. So I'm going to sub b equals 3 into equation 1. So take equation 1. I've got negative a plus 2b, but b is 3, so I put a 3 there, is equal to 4. So negative a, got a 6 there, subtract it from both sides. I get negative 2 here, and then just divide by negative 1, I get a equals 2. So there's my second scalar, and I now know the unique combination of these two vectors that will give me the vector with components 423. So just to make it official, I'll put the actual linear combination of those two vectors. So 2 times vector negative 1, 4 plus b is 3 times vector 2, 5. That's going to give me the vector with components 423. And you can quickly check it here. You got negative 2 plus 6 is 4. You have 8 plus 15 is 23. So that works. And there's only one combination that works. It's a unique solution. Okay. So now we're going to try two other base vectors, or hopefully spanning vectors. Well, not spanning vectors, vectors that will give us a linear combination of these two vectors that will give us 423. So again, set it up the same way. So a times the first vector plus b times the second vector should give us the vector x, which is 423 components. So same way, first we do the x components, so I get a minus 2b is equal to 4, first equation. And then for looking at the y components, I got a times 0, so that's just 0. And b, well, this is going to work out nice because it gives me b is equal to 23. So not much solving required there. And now we're going to sub, I guess I could call that my second equation, but I don't really have to work with these two other than substitute in b equals 23 into the first equation. So a minus 2 times 23 is equal to 4. So a minus 46 equals 4. So add 46 to both sides. We get A equals 50. So there's the second scalar multiple that we need to create vector x. So again, I can write that out. So A is 50 times the first vector's components plus 23 times the second vector's components is going to be equal to 423. And again, we can check it out. 50 plus negative 46. 50 minus 46 is 4. And this would be 0. This would be 23. And that's correct too. So we know what's correct, and it's also unique. There's no other combination that creates that vector. Okay. Let us try this example. It says show that the set of vectors 2, 3, and 4, 6 does not span R2. And we learned at the first page that any two vectors will span R2 as long as they're not collinear. So we either prove they're collinear or prove they're not collinear, and then we have our answer. So we can actually, you can see this very apparently, since you can write the second vector, 4, 6. You can very easily see it's a scalar of 2. Since I can write one vector as a scalar multiple of the other, the vectors are scalar multiples of each other, and therefore cannot span R2. Excuse me. Okay, if we couldn't show that they were scalar multiples, that would also prove that they do span R2. So it's that's the if and only if part of the statement. So if one thing is true, then the other thing is true. If one thing's false, the other thing is false. Okay, so that's a pretty quick little proof there. Example 4. This one's it looks similar to the first two examples. Show that the set of vectors 2, 1 and negative 3, negative 1 is a spanning set for R2. So this is basically saying you should be able to create any vector in R2 from a linear combination of these two. So in terms of setting this up, it looks like it's the same. We start with a scalar multiple A, multiply with the first vector, plus B times the second vector. Now instead of actually having a desired vector here, we actually leave this very generic as just x, y. We want to be able to create any combination of x, y from these two. Okay, so it continues the same. We set up a linear equation for both the x component and the y. So we get 2a minus 3b is equal to x, first equation, and then we get a minus b is equal to y. Now what we want to try to do is kind of turn this around so that we have two equations, one for a and one for b. So we're basically, in a sense, we're not really solving for a and b. We're not going to get a numerical answer for a and b because it'll change depending on what x and y are. So what we want to do is show that we can actually create any possible combination of x and y and show how we do that. So I still want to isolate one of the variables, and it looks like if I just multiply the second equation by 2, then I can cancel the a's. So equation 2 times 2 gives me 2a minus 2b equals 2y. So that's really our third equation. It comes from 2. And now what I'm going to do is subtract. I'm going to take equation 1 and subtract equation 3. So 1 minus 3. If I look down here, 2a minus 2a, nothing, just like we planned. Negative 3b minus negative 2b, which is negative 3b plus 2b, so that would be negative b, and then x minus 2y on the right side. Okay, now I could just divide, if I want b by itself, I'll just divide everything, or multiply everything by negative 1, so that turns into b equals 2y minus x. And that's the first equation I want, but I want an equation like this for a, so now I'm going to sub this into, so I'm going to say sub b into equation number 2. So equation number 2 was a minus b, so I'm going to put a set of brackets where b is and plug in what b's actual value is. 2y minus x is equal to y. So we've got a new version of equation 2 with our value of b plugged in. Okay, now if I think I can create an equation directly from here, so that would be a minus 2y plus x, and if I add 2y over here, I get 3y, and then I have to subtract x from both sides, so that would be negative x plus 3y. So there's my two equations for a and b. Okay, so I can say, since we can find values for a and b, for all values of x and y, we can create any vector in R2. Therefore, these vectors span R2. Okay, so how that works is if, say I wanted to create the point 5, 10. Sorry, not the point, the vector with components 5, 10. So I know that I want my x to be 5 and my y to be 10. So I just plug those values, x equals 5, y equals 10. I would get, be 20 minus 5, b would be 15, and this would be negative 5 plus 30, a would be 25. So I can then take those values of a that I just calculated from given my x and y, and I can go back to the initial equation here, and I put my 5, 10 here, and the values of a that I calculated. So you could easily show this as, this is kind of like a generic proof for any possible x, y combination of values for the components, and you can show all you need is the x and y, and you can create the a and b values from these two formulas. Okay, so it's kind of an interesting proof that you can prove for all possible, not just one possible, but for anything. Okay, one more example, and this is a long one, just to let you be aware of that. We find a nice sharp pencil for this one. So the title is, and it kind of tells you what we're trying to do, determine if three vectors lie in the same plane. This is a pretty standard question, so knowing how to do this is important. Okay, so given the two vectors a and b with the components given there, does the vector c with those components lie on the plane determined by a and b? You notice we've jumped obviously to 3 space because we've got our 3 components, x, y, and z. So how do we go about this? Well, it basically starts off the same way as the previous 3 questions did, or at least 3 of the previous questions. So I've got my 2 vectors, actually 3 vectors, a, b, and c. I want to show that a linear combination of a and b can create vector c. So I set it up the same way. This time I'll use, because I've got a and b as my vector names, I don't want to use those as my scalars as well. It'd just be too confusing, so I'm going to use k and m. So basically, if I have a scalar k and I multiplied vector a's components, so -1, -2, 1, and then I add a scalar multiple of b, so I'll call that scalar m, and then multiply with b, so the components 3, -1, 1. What I want to be able to do is create this vector -9, -4, 1. Now, you can see this is going to be a little different because I am actually going to be creating 3 equations, one for the x component, one for the y, one for the z. So let's do that. So when I multiply for the x component, I get -k plus 3m is going to be equal to -9. Okay, so there's my first equation. And I'm going to kind of do these little vertical lines just to separate them. Second equation, looking at the y component, I've got -2k minus m is equal to -4. Equation number 2. And then the third equation for the z component, I've got k plus m is equal to 1. Third equation. That's right. There you go. Okay, now this is a bit different because we've only got 2 variables, k and m, that we're looking to find, but we've got 3 equations, so we're not really used to doing that. So the way we do these questions is we use 2 of the 3 equations to find the solution for those 2 equations for the values of k and m, and then we take that solution, we plug it into the third equation that we created and see if it satisfies that equation. So we'll always be able to find an equation for 2 of the equations. Well, not always, but most of the time. And then once you plug that solution into the third, you can check to see if that combination works for all 3 equations. So you don't necessarily have to pick the first 2. You kind of eyeball this and work your way through. So this equation here seems pretty simple because I can just isolate k and m very quickly. So what I'm going to do is just isolate for k. K is going to be equal to 1 minus m. So I didn't really do anything with this equation other than just rearrange it. So I'm going to plug in that value for k over here for the first equation. So I'm just going to say sub in k equals 1 minus m, and then I'm going to do that. So if I sub in k equals 1 minus m, so negative of that would be -1 plus m. So -1 plus m plus 3m is equal to -9. You can see now I've just got one variable in this equation. That means I'm going to be able to solve for it. Combine the m's together, I get 4m. Add 1 to both sides, -8. And very quickly we've got a value for m. M is -2. Now, I'm just going to plug that value of m back into equation 3, which is nicely set up to give us k. So substitute m equals 2 into equation 3, well, the altered version of equation 3. So that would be k is equal to 1 minus m. So m is -2. So that gives us k is equal to 3. So we've got a solution. So let me just formalize what we've just found here. So the combination of k equals m equals 2 is a solution for equations 1 and 3. So we've done our first part. We've basically got a solution for these two equations. And now what we do is we take this solution and we plug it into equation 2. So I'll just put a note here, sub into 2. So negative 2k is -2 times 3 minus m, which is -2, is equal to -4. And we get -6 plus 2 is equal to -4. -4 equals -4. That is definitely a true statement. So therefore, this solution for equations 1 and 2 also works in equation 3. So works for 2. So now it works for all 3. So therefore, let me just get a little room here. Therefore, I can now set up my linear combination because I know the values of k and m. I just plug them into here. Therefore, 3 times -1, -2, 1 plus m is -2, so I'll change that to a minus sign, -2 3 -1, 1 is equal to the vector we were looking for, -9, -4, -4, 1. And again, we can check this. -3 minus 6 is -9, true. -6 plus 2, -4, and 3 minus 2 is 1. So confirmed that it works. Okay. Now, the second part here says, does the vector -9, -5, 1 lie in the plane determined by those first two vectors, A and B again? And you could do exactly what we just did all over again. Let's set up the equation just so we can. So we have part B, see there, okay. K times -1, -2, 1 plus m 3 -1, 1 is equal to, and now we actually change the value from not -9, -4, 1 to -9, -5, 1. Okay, so this is what's changed in our equation. So the only equation that we created in part A that's going to be different is the equation for the y component, which is the middle, the second equation. So instead of it being -2k minus m equals -4, this is now going to be -5. So I could put that in words here. Same equations for 1 and 3. Now the new equation for 2, equation 2 will look like this. -2k minus m equals -5. So I'll call that my new equation 2. And if this point is on that same plane, I should be able to plug in my k and m values that I got above. So k equals 3 m equals -2, because that was a solution not only in the above question, but for the equations 1 and 3 here. So that would be my solution for equations 1 and 3. But now you can see if I plug that in here into this equation 2, the revised equation 2, I'm going to have -2 times 3 minus -2 equals -5. So -6 plus 2 equals -5. Well, that's definitely not working this time. So this is not true, which you could probably predict because the only thing that changed was that number, so the left side was still the same. Therefore, our conclusion is the vectors are not on the same plane. Okay, so full page of work for that two-part question. Hopefully it makes sense. I think if you could see the fact that you've got 3 equations for 2 variables, you're not solving for 3 equations with 3 variables. So you pick 2, you solve for the 2 variables, and then take that solution, plug it into the third equation, see if it works. And if it does work, that means you can create a linear combination of the first 2 vectors to create the third vector, which means in the case of 3 space that third vector is on the same plane. Okay, and if you can't plug in the solution into the third equation like we couldn't here, if it doesn't work for the third equation, that means they're not on the same plane because I can't create a linear combination of those 2 vectors to create this third vector. Okay, so that's spanning sets and linear combinations. Hopefully that makes sense. Some homework questions here to try out these new techniques and types of problems. And I believe that's it for this first unit. So until we get to the next unit, I hope you have a great day, and I'll see you in the next lesson.